All right, buckle up, everybody, because today we're diving deep, way deep into the cosmos.
Oh, this is going to be good.
It is. We're talking about how we find our place not just here on Earth, but out there in the vastness of space.
So like a cosmic GTS.
Exactly. We'll be exploring how we pinpoint locations, figure out the reasons behind those awesome Earth seasons, and even unravel the secrets of the moon. And to guide us, we're turning to Chapter 4 of The Earth, Moon, and Sky by Ramesh Dongana.
Sounds like a plan.
Okay, let's kick things off with something we use every day without even thinking coordinates. I mean, yeah, I know they help us find places on a map, but I've always been a little hazy on how they actually, work.
You know, you're not alone there. It's easy to just take them for granted.
Totally. So help me out here.
Okay, so think of it like a massive grid system, right? It's laid over the entire Earth. And we use those numbers you see on maps, latitude and longitude, to pinpoint any location.
Okay, that rings a bell. But remind me, which one's which?
All right, so latitude tells you how far north or south you are from the equator. Like the equator's 0 degrees latitude.
Gotcha. So the higher the latitude number, the farther you are from the equator.
You got it. The North Pole is 90 degrees north. The South Pole, 90 degrees south.
And longitude.
Longitude tells you how far east or west a location is from a special line called the prime meridian.
Ah, the prime meridian. Didn't that go through, Greenwich or something?
Right through Greenwich, England, runs from the North Pole to the South Pole.
Okay, so if I've got a location, say Denver, Colorado, and its coordinates are 39.7392 degrees N, 104.9903 degrees north.
Yeah.
What does that actually tell me?
Well, that's like Denver's cosmic address. 39.7392 degrees north means it's that far north of the equator.
Okay.
And 104.9903 degrees west. That means it's that far west of the prime meridian. Boom, you've got Denver.
It's kind of like a universal language for finding any spot on Earth. But
Right.
what about when we look up? We can't exactly draw lines on the sky, can we?
You're right, we can't. But, astronomers are clever folks. They came up with something pretty amazing. Imagine taking Earth's grid and projecting it outwards, like onto this giant sphere surrounding our planet. That's what we call the celestial sphere.
So it's kind of like an imaginary globe, but with stars instead of continents.
Exactly. And instead of latitude and longitude, we use declination and right ascension. Those are our celestial coordinates.
Declination, is that kind of like latitude for the stars?
You're catching on quick. It measures how far north or south a star is from the celestial equator.
And the celestial equator is?
Just Earth's equator, but projected out onto the sky.
Cool. Okay, so what about right ascension? Is that like the celestial version of longitude?
Spot on. It measures how far east a star is along the celestial equator. But here's the kicker. We start measuring from a fixed point called the vernal equinox.
The vernal equinox, hold on, remind me what that is again.
It's one of the 2 points where the sun crosses the celestial equator each year.
Oh, right. It's like the start of spring, right?
Yep. So if a star has a high right ascension, it means it's farther east on the celestial sphere. It's kind of like saying it's later in the celestial day.
Wow. So with declination and right ascension, astronomers can pinpoint any star, just like we find spots on Earth.
Exactly. It's like having a map for the entire universe.
That's incredible.
Mm-hmm.
But there's another set of coordinates we use here on Earth, right? Azimuth and altitude.
Oh, yeah. Those are super handy for figuring out where things are in the sky right now.
But I always mix those up.
No worries. It's actually pretty simple. Imagine you're standing outside looking at the sky. Altitude tells you how high up something is.
Like degrees above the horizon?
Yep. 0 degrees is right on the horizon. 90 degrees is straight up.
Okay, that makes sense. And azimuth.
Azimuth tells you which direction to look. We start at north, that's 0 degrees, and then go clockwise. East is 90, south is 180, and west is 200.
So if I see a bright star rising in the east, it would have an azimuth of about 90 degrees.
You got it. And if it's, say, halfway up the sky, its altitude might be around 45 degrees.
Okay, that's actually way clearer than I thought. It's amazing how we use these systems to find our place, not just here on Earth, but in the vast universe.
It really is. It's like we're all connected to this cosmic grid.
Totally.
Yeah.
But let's shift gears a bit. Let's talk about something we experience every day, seasons. Why do we have these distinct periods of, warmth and cold throughout the year?
Well, it's not because Earth gets closer to the sun in the summer and farther away in the winter. That's a common misconception.
Really? So what is it then?
It all comes down to our planet's tilt. Earth's tilted on its axis at about 23.5 degrees,
Okay.
and that tilt stays the same as Earth orbits the sun. So different parts of our planet end up getting varying amounts of direct sunlight throughout the year.
So when a hemisphere is tilted towards the sun, it's summertime there.
Bingo. That hemisphere gets more direct sunlight, leading to warmer temps and longer days. The other hemisphere, it's tilted away, so it's winter there, cooler and with shorter days.
Okay, makes sense. But what about all those terms we hear, equinoxes and solstices? What are those exactly?
Those are like milestones in Earth's journey around the sun. They mark specific points where the tilt has a really noticeable effect.
Okay, break it down for me.
Let's start with the solstices. Those happen when the Earth's axis is tilted the absolute most towards or away from the sun. That's when we get our longest and shortest days of the year.
Right, the summer solstice is the longest day, and the winter solstice is the shortest.
Exactly. The summer solstice, usually around June 21st, is when the northern hemisphere is tilted most towards the sun. And the winter solstice, around December 21st, is when it's tilted farthest away.
And what about those equinoxes?
The equinoxes are like the balancing points. They happen when neither hemisphere is tilted more towards the sun than the other. They happen around March 20th and September 22nd.
Okay, so day and night are roughly the same length then.
Pretty much. The vernal equinox in March marks the beginning of spring in the northern hemisphere, while the autumnal equinox in September kicks off fall.
It's amazing how this tilt, this one little thing, creates such massive changes. It really puts things in perspective.
It's like a cosmic ballet, isn't it? This interplay between tilt and orbit. And speaking of keeping track of these cosmic movements, maybe we should talk about how humans have measured time throughout history.
Now we're talking. From ancient sundials to today's super accurate clocks, I'm all for exploring the evolution of timekeeping.
All right, then, let's go back in time a bit. It's pretty mind-blowing when you think about it. We've gone from simple sundials to these crazy, precise atomic clocks. Talk about a glow-up for timekeeping.
It is amazing. Humans are so ingenious. But I've always been kind of fuzzy about the different ways we actually measure time. Solar time, sidereal time. It all gets a bit jumbled in my head.
Oh, yeah, there are a few ways to slice it. Let's start with what we usually call a day, 24 hours.
The good old 24.
Right. That's based on what we call a solar day. It's the time it takes for the sun to appear back in the same spot in the sky.
So like from noon one day to noon the next day?
Exactly. But now, get this, there's also something called a sidereal day that's based on Earth's rotation relative to the stars, not the sun.
Hold up. A different kind of day.
Yep. And it's a smidge shorter than a solar day. About 23 hours, 56 minutes, and 4 seconds.
Wait, why is it shorter? Shouldn't a full rotation be a full rotation?
Good question. But remember, as Earth spins, it's also moving around the sun. So when Earth completes one spin relative to the stars, it's also scooted a bit along its orbit. So to catch up to the sun and have it look like it's back in the same place, our planet needs to rotate a tiny bit more. Those extra few minutes make up our solar day.
Wow, that's some cosmic trickery. So two kinds of days, one for the sun, one for the stars.
Yeah.
But why do we even need sidereal time? Does it affect our daily lives?
Not directly, no. But for astronomers, it's crucial. They use it to pinpoint where stars and other objects are in the night sky at any given time.
So it's like their own special time zone.
Pretty much, like a celestial clock that's synced up with the stars.
That's so cool. Okay, well, while we're talking about different ways of measuring time, let's tackle calendars. How do we go from tracking time with the sun and stars to the calendars we've got today?
Calendars are like this fascinating history of how humans have tried to wrangle the sun, the moon, and the stars into something that makes sense. A lot of ancient cultures base their calendars on the movement of celestial bodies. Like the ancient Egyptians, their whole calendar revolved around the rising of the star, Sirius.
Sirius? What's special about that star?
Well, for the Egyptians, its appearance coincided with the flooding of the Nile River. That was a huge deal for them, agriculturally speaking.
So they were basically using the stars to predict the future. That's incredible.
Right. And then there's good old Stonehenge, that mysterious monument in England.
Oh, yeah. Big, spooky rocks.
Exactly. A lot of researchers believe it was used to track the solstices and equinoxes.
Wow. So many cultures, all using the sky as their guide.
Totally. And as civilizations got more complex, they had this challenge, how to make a calendar that synced up both the solar year and the lunar month.
Right, because the lunar month is about 29.5 days, but the solar year is about 365. Not exactly a match made in heaven.
Nope. And that little mismatch led to like a whole bunch of different calendar systems. Some are lunar, some solar, some a combo of both. Like the Islamic calendar, strictly lunar, months begin with the new moon.
Okay, so totally different from what I'm used to.
Yeah. Then there's the Jewish calendar that's lunisolar. It tries to keep in sync with both the sun and the moon.
It sounds complicated.
Oh, it can get pretty intricate. And then there's our calendar, the one we use in most of the world today, the Gregorian calendar.
Mr. Gregorian must have had his work cut out for him.
Well, it actually went through a few rounds of edits. It's got roots in the Roman calendar, which was a mess. Then Julius Caesar came along and gave us the Julian calendar, 365 days, with a leap day every 4 years.
Leap years. Always tripping me up.
I feel you. But even the Julian calendar had its flaws. It drifted out of sync with the solar year over time. So in 1582, Pope Gregory III decided to tweak things. That's where the Gregorian calendar comes in. It's got a more complex leap year system to keep it aligned with the sun.
So that's why we have all those weird leap year rules.
You got it. It's all about keeping us on track with the cosmos.
Amazing. Centuries of work, all to make sure our calendars reflect the cycles of Earth and the sun. It makes you appreciate those little squares on the wall a bit more, huh?
Absolutely. But hey, while we're on the topic of celestial cycles, let's talk about our celestial neighbor, the moon. Its phases, its motion, those incredible eclipses we see, it's all connected.
The moon is definitely a captivating neighbor. Always up to something interesting.
You said it.
Okay, so let's talk about those moon phases. I know they have something to do with how much of the moon is illuminated by the sun, but I've never quite wrapped my head around it.
Right. It can be kind of tricky to visualize.
It really can.
Well, it's all about where the moon is in its orbit around Earth relative to the sun. As it travels around us, the angle at which sunlight hits it changes. So from our view here on Earth, the illuminated part looks different throughout the month.
Okay, so like when we see a full moon, that's when the sun, Earth, and moon are all lined up with Earth in the middle.
Exactly. The sun's shining directly on the side of the moon facing us, so we see the whole thing lit up.
And what about a new moon? That's when the moon is, like, totally dark.
Right. During a new moon, the moon is between the sun and Earth. The side facing us isn't getting any direct sunlight. It's basically hiding in the sun's glare.
Gotcha. Okay, that makes sense. But what about all the phases in between, like the crescent moon, the quarter moon? How do those fit in?
Think of it like this. As the moon goes from new to full, we see more and more of it illuminated. That's called waxing. And as it goes from full back to new, we see less and less. That's waning.
So it's like a gradual reveal, and then it slowly disappears again.
Exactly. And those quarter moons you mentioned, they happen when we see exactly half the moon lit up.
Okay, starting to click now. This is good stuff. But here's another thing that's always boggled me. The moon always shows us the same face. Does that mean it's not spinning?
It is spinning, but here's the twist. It rotates at the exact same rate that it orbits Earth. We call that synchronous rotation. That's why we always see the same old craters and features.
So is there really a far side of the moon that we never see?
There absolutely is. And just to be clear, it's not actually a dark side. It gets as much sunlight as the near side, just never at the same time. We just never get to see it from Earth.
Whoa, that's wild. Okay, so what about the moons, like rising and setting times? Those seem to change a lot throughout the month, too. What's up with that?
Well, as the moon orbits us, it moves a bit eastward relative to the stars each day, so it ends up rising about 50 minutes later each day.
Oh, okay. So like a full moon rises at sunset and sets at sunrise.
Yep. First quarter, moon rises around noon, sets around midnight. It all depends on where it is in its orbit.
That's why you sometimes catch the moon out during the day. Makes sense. All right, now for the really dramatic stuff, eclipses. What causes those moments when the sun or the moon seems to, like, vanish?
Eclipses are basically cosmic shadow puppets. They happen when the sun, Earth, and moon line up in a very specific way. A lunar eclipse happens when Earth gets right between the sun and moon.
So Earth's shadow falls on the moon.
Exactly. Blocks the sunlight from hitting it. And that can only happen during a full moon.
Spooky. And a solar eclipse is when?
A solar eclipse is when the moon gets between the sun and Earth, casting its shadow on part of our planet. And that can only happen during a new moon.
Wow. So we've got a whole lot of moving parts up there. But if they're always doing their thing, why don't we have eclipses every month?
Ah, good point. It's because the moon's orbit is tilted a bit relative to Earth's orbit around the sun. Most of the time, that tilt means the shadows miss each other. Eclipses only happen when everything aligns just right.
It's like a cosmic lottery.
Kinda, yeah. But we can actually predict them pretty accurately using something called the Saros cycle. It's a pattern that repeats every 18 years, 11 and a third days.
That's incredible. So much order in what seems like chaos. This whole deep dive has been amazing. We've covered so much ground. We figured out how we find our place on Earth and in the sky, learned about what causes seasons, and even uncovered the secrets of the moon.
It's been a wild ride, for sure. It really makes you realize just how dynamic our universe is.
Absolutely. And for all of you listening out there, we hope this has left you even more curious about the cosmos. Don't stop exploring. Don't stop asking questions. And thanks for joining us on the Deep Dive.